Moving on to the problem part, here model question paper problem. It is given as in the model question paper, find the GSOP. Here find the set of the orthogonal pair. We are having three pairs. One is of signals, that is S1 of t, S2 of t, and as S1 of t, S2 of t, and S3 of t. Okay, now here you need to find the set of orthonormal function and also express each signal in terms of the set of basis function you need to define. So firstly, you have to write n is equal to, or m is equal to 3 and phi 1, phi 2 and phi 3. We need to find. So firstly, phi 1 of t, as I said earlier, this is the formula. This is the formula you need to know for all the problems related to this. In this, first we'll write it as even. Even we need to find here even, we don't know. So that is the integration of 0 to t s1 square of t into dt. What is s1? To find here, limit is from 0 to t. So here x-axis is from 0 to 1. So our limits is from 0 to 1. S1 square of t means it is the amplitude. That is how much here 2. So it is 2 square. So our energy is 4 joules. So similarly, calculate the phi 1 of t, that is s1 of t divided by square root of 4, that is 2. So it is half s1 of t. Remember it. Half s1 of t means what? This is our s1 of t that is given. So you need to half the amplitude. So doing half the amplitude, we get the phi 1 of t as like this. So you need to represent it as, so phi 1 of t is from 0 to 1, where 1 is from 0 to 1. Otherwise, it is 0. So next is phi 2 of t. Phi 2 of t, here we know you need to know this equation. So here the new variable g2 of t is independent of phi 1 of t. So it is interval as 1 to 2. So now you need to calculate that. To calculate that, you need this formula. So this formula in this g2 of t is s2 of t minus s21 of phi 1 of t. So for this, you need this part. So first you need to know even this formula. Here S21 is equal to integration of 0 to t, S2 of t, phi 1 of t into dt. So what is S2 of t? So in the equation, in the graph, you can observe S2 of t is what? It is minus 4. See here, it is minus 4. So minus 4 into 1. Into 1 is phi 1 of t. We got it as 1. So you get it as minus 4. That is S2. Now substitute that here. You get it as S2 of t minus into minus is plus phi 1 of t. Now you need to write G2 of t in terms of graph. How do you write it? Firstly, you need to write S2 of t. This is the given question S2 of t, and this is our phi 1 of t. So phi 1 of t, you need to multiply it 4. So multiply 4, the amplitude becomes 4. Now for these two, you need to combine these two and write a graph here for G2 of t. So you can observe here, one is, we are having two parts. First consider from 0 to 1, then 1 to 2. For 0 to 1, it is, you can observe, the amplitude is 4. Here it is minus 4. Here it is minus 4. So plus 4 and minus 4 will get cancelled. So you will not get anything between 0 to 1. But from 1 to 2, here it is 0 and here it is minus 4. So hence we get it is minus 4. This is how you have to do in all the problems. You need to combine two graphs and write it here. So finally you got this expression graph G2 of t. What you need to find? Phi 2 of t. For that, we got the numerator. We need to find the denominator, which is our energy. Energy, see here from where to where is the limit? 0 to 2. So 0 to 2, what is the amplitude? It is minus 4 square. So substitute it, you get it as 16 joules. So 16 joules. So what will be my phi 2 of t? It will be G2 of t divided by 4. So for this graph, you need to divide it by 4. On dividing it by 4, you get this one as minus 1. So finally, in the step 3, where I is equal to 3, same equation, you need to know this general equation. Substitute I is equal to 3. On substituting I is equal to 3, J1 to J2, you need to split it into two parts. So S3 of t, S31, phi 1 of t, S32, phi 2 of t. So first we'll find out this and then we'll find out this. So S31 is 0 to t, S3 of t into phi 1 of t. So S3 of t, this is given in the question, and phi 1 of t, we have find it out. So what do you get? Here the limit will be from where to where. Here actually you're having 1 and 2. You're having 1 and 2. So where do you have to consider from 0 to 1 because it is common. Here also we are having 0 to 1. Here also we are having 0 to 1. So integration limits will be 0 to 1 and the amplitude here is 3 and here it is 1. So it is 3 to 1. 3 into 1 is 3. This is our S32. Similarly, come here. This is given in the question and this is what we had find it out last time, phi 2 of t. And here, what are the limits you need to consider here? Here, again, 1 and 2 is there. So from 0 to 1, here it is nothing. So you need to consider from 1 to 2. 1 to 2. And what is the amplitude here? It is 3 and here it is -1. Multiply, you got this. Substitute these two values in this equation. You get the G3 of t. Take those 3 common out and you simplify. So you need to represent now the G3 of t in the graph. So firstly, you need to minus phi 2 of t and phi 1 of t. You minus the two graphs what we have got here. Similarly, as I explained, you will get this graph. So for this, you need to multiply amplitude with 3. So you will get it as -3. So this and this is given in the question. So now what you have to do, you need to add these two. You need to add these two, you will get this. Similarly, taking the graph here, here it is 1 and here it is 1 and here it is 2. So from 0 to 1, it is -3, it is 3, that gets cancelled. So nothing comes between 0 to 1 here. And next from 1 to 2, it is -3 here. From 1 to 2, it is 3 here. So we get this as 1 to 2. Again, that gets cancelled. So finally, from 2 to 3, here it is 0, but here it is 3. So 0 plus 3 is 3. So that how we get this. So finally, in the expression, we need to find out the energy by G3 of t whole square. So this amplitude is 3. So 3 square is 9. Now that is 9 joules. Substitute it and we get our G3 of t is 1 by 3. G3 of t as our phi 3 of t. Represent that in the graph. So this is our phi 1 of t, this is phi 2 of t and phi 3 of t. So hence you can observe from 0 to 1 it is 1, from 1 to 2 it is -1, from 2 to 3 it is +1. So the graph is not having no overlapping. So all these three are the orthogonal to each other and they have a unit energy, hence they are called as orthonormal. Hence they are called as orthonormal. Next is as I said before, the n is nothing but it is a number of basic functions that we need to find out, and number of independent signals that is given as m. The both are here. These are s and these are phi. Step 4 is you need to write them in terms of the basic function. So how do you write S1 of t? We know phi 1 of t is S1 of t by 2 that we had got it earlier. First multiply it here. So you get it as S1 of t 2 times phi 1 of t. So representing that in the graph, what you have to do is phi 1 of t graph, you need to double the amplitude. 1 I had got previously. I made it as amplitude 2. Similarly, S2 of t, you got this expression, multiply it and change this graph according to this equation. And phi 3 of t similarly. So next in the same way, in the December Jan, they have asked the same question with the different graphs. So here n is equal to 2. So here we need to find phi 1 of t and phi 2 of t. So phi 1 of t, this is the expression, find out the energy and write the graph from where to where it varies. And in the step 2, you need to find G2 of t, where your S21 and then the S2, you find all those things and substitute back into that along with the energy. You get the phi 2 of t, that is 1 by 3 times the G2 of t. In the step 3, as the phi 3 of t is not there, it is 0. You can say these both phi 1 of t and phi 2 of t are 0. So on substituting also we get it as 0. So finally you need to find S1 of t equation, S2 of t equation and S3 of t equation and represent them in the graph. So you need to represent S1 of t, S2 of t, S3 of t as phi 1 and phi 2. Next, coming to the other part, conversion of continuous AWGN channel in a vector form. Let's consider this equation where x of t is a noisy channel R at the receiver, that is receiver, and Si of t plus omega of t. This omega of t, it is a sample function of the wide Gaussian noise process. This can be represented as when you give a transmitter signal Si of t along with a white Gaussian noise, then you get the received signal X of t. So considering the output of the correlator has a random variable and it is defined as xj is 0 to t, x of t, phi j of t. So it is given by, you can write it as Sij plus omega j. So where Sij is the deterministic component of xj and the omega j, it is a sample value of the random variable. So finally you can write xj as xij. This xij, you can write it as 0 to t, Si of t into pi j of t, omega j, you can write. Consider this equation 3 and equation 4. So here we are having a new process where x dash of t, it is a sample function of the representation of x dash of t. So x dash of t is equal to what? X of t minus summation of j is equal to 1 to n xij pi j of t. This is a equation 5. So now you need to substitute the equation 1 and equation 2 in 5. And substituting that, we get this part Sij, as it is minus, it gets cancelled, and we remain with this. So this can be represented as omega dash of t. So hence we get x dash of t is equal to omega dash of t, where this x dash of t, it depends on the noise omega t at front end of the receiver and not all on the transmitted signal SRT. Thus, you can say it is a random process which is expressed like this. So x of t, it is given like this, where you can change x dash of t as omega dash of t with the random process. So from the above equation, we can conclude that the correlator's output, that is from xj, j is equal to 1 to n, with each xj is a Gaussian random variable and is characterized completely by its mean and variance. So this one part is done. And next we will move on to the optimum receivers of the coherent detection. So the first one is ML function. The first one is the ML decoding. Here the maximum likelihood decoding. Let us consider, as I said, m possible signals S1 of t, S1 of t, like that till the Sm of t. It is transmitted with an equal probability of 1 by m for the t seconds. So let Si of t, it is applied to the bank of correlators with a, which is having a common input and appropriate orthonormal basis functions yielding the output of S0 of 1. So now as x of t is corrupted by the noise omega of t, if applied to the bank of correlators, this defines an observation vector of x. So the relation between the observation vector as well as the signal vector Si is given like this. So here this is my Si, that is signal vector, and this is my observation vector. So finally you can see, you can observe this is the noise of vector W. This is our received point, received signal point. Next, we'll move to the signal detection statement. So here, given observation vector x is performing a mapping from x to estimated m cap of the transmitted signal mi in a way that would minimize the probability error. It will minimize in the decision-making process. So let us consider the observation vector as this x. Suppose the decision-making is made m cap as mi, then you can see the average probability of the error detection is given by P of MIK is equal to 1 minus MI cent by X. So to minimize the probability error, we state here the optimum decision has MI is equal to MJ. So that should be, as I said, this MI, this should be greater than or equal to this K, where our K is not equal to I and 1, 2, 3 till M. So this is called as mapping, that is maximum posterior probability, a posterior probability. For k is equal to I, if this becomes k is equal to I, then you can say m dash of mj. If it is pi k, fx of x by mi will become fx of x. This will be considered as equation 2. And next, you can observe it as fx of x by mi. It is the conditional probability density function of a random observation vector and transmitted symbol m of k. F of x is an unconditional probability density function of x. And now, if you state that of the decision making in terms of this, you can write m cap is equal to mi. Then it is maximum for k is equal to m. Then thus the maximum likelihood decoder computes log likelihood function has a matrix for all the m possible managed symbols and compares them and decides in favor of maximum. Next is the graphical representation of the decision rule. Here, what we learned now, we will be representing it in the graphical, how it's the decision made. This is how it is. Here, observation vector X lies in the Z region. Here this is our region Z1, region Z2, region Z3, and region Z4. Here square root of E, square root of minus E. Here it is square root of E and minus 40. This is the decision boundary what we need, and this will be our message points. So here observation vector exit lies in the Zi if the Euclidean distances, as I said, the space that we had, signal space that we had discussed. On squaring that, you need to square this. We get this as one part, second part, and third part. Similarly, the first term is neglected because it is independent of k. K is not there here. The second term is an inner product of the observation vector x and transmitted signal xk. So the third term is transmitted signal energy, that is ek. So finally, ek is given in terms so like this. So hence you can say the maximum likelihood decision is stated by observation vector x lies in the region xi if it is k is equal to. Next is the important part, that is correlation receiver. For an AWGN channel, when it is transmitted, signals are equally likely. Optimal receiver, which minimizes the average probability of the error, is a correlation receiver, which consists of two parts, part 1 and part 2. It is a bank of n correlators whose output is x, and another one has signal transmission decoder whose output is x, means here detector and the demodulator both are there here, which is given, and this is a bank of correlators as I said. The first part is part 1. Here, as I said, here it is bank of correlator. X of t is given along with phi 1 of t, phi 2 of t, phi n of t. And then we send to the integrator where we get a x1, x2, and xn signals. So these are our observation vectors. And this phi 1, phi 2, these are our orthonormal basis functions, this phi 1, phi 2. In the part 2, as I said, signal decoding part. Here x is given, so along with the signal S1, S2, and Sm, these are our inner product. So that is sent to the accumulator. In the accumulator, we use summation along with the minus g, half the g, along with the output of this accumulator. Finally, in the selector part, it takes the decision and it gives the maximum likelihood decision takes place here, and we get the estimated m cap. So that here minus half is given as it subtracts the half the signal energy. So hence we get the output. So this was about the correlator. Next we will move on to the matched filter receiver. Here matched filter receiver. Here the correlation receiver requires analog multipliers and the local references of the orthonormal functions, that is phi 1 and phi 2 till phi n, which are the times synchronized with respect to the transmitted signal, which can be avoided if the filter with appropriate impulse response are used. Consider an x of t. This is a received signal and we are sending it to xg of t, which is LTI with a impulse response of xg of t. We get an output of yj of t, which is an output. So here I of t, it is given as integration of minus infinity to x of 2 hj of t minus 2. Integrate over the observation of the transmitted signal from 0 to t, then it becomes capital T to minus t, yj of t. So now we can detect the based on the bank of correlators output, jth correlator. For the jth correlator, you can write it as phi j of t. For that xj of t, finding out that. So finally, our equation on equating that to yj of t will be equal to our xj of t. So finally, you can write it as xh of ct is equal to phi j of t. So this completes the module 1 of the digital communication. So to motivate me to do the further modules or to continue doing it in the further subjects, so you need to subscribe to my channel. I want your response in the subscribing. So please do like, share, and subscribe to Exam Ignite YouTube channel for the further videos and notes. Thank you for watching. Do like, share, and subscribe it without forgetting. See you in the next video.